Okay, let's look at this problem. This is a traveling wave. We're now looking at, we were just looking at simple harmonic motion before, and now we're looking at traveling waves. So this equation, the traveling wave equation, if you look at it, you might say, well, it's a little bit like the simple harmonic motion equation. And sure, there's a reason for that, of course. It's that the particle in the medium, so if you consider I don't know, let's consider maybe a water wave, first of all. So a little particle of water, as there's a wave traveling, the disturbance of a wave traveling through the water, the particle of water is going to be moving in simple harmonic motion. So say it'll be moving, oscillating up and down in simple harmonic motion, whereas the disturbance, the wave itself, is going to be traveling horizontally through the water, right? That's a transverse wave example. A longitudinal wave, of course, you'd have the simple harmonic motion of the medium, particle in the medium would be oscillating parallel to the axis along which the wave is moving. Okay, so be sure, I'd say before you really start in on these problems in this chapter, be sure that you have a good picture of what the particle is doing, the medium is doing, versus what the disturbance is doing. Unless you can separate those things out and kind of be able to see what each one is doing, it makes it really hard to understand what's going on with these wave functions. An example that I often will give in class is an example of like a stadium wave. I know this is cheesy, but just hang with me for a second. So, like at a football or baseball stadium or whatever, um, what happens is that their people like stand up and then sit down, right? When it's at the right time. They have to do it when it's their turn. So what you see is you see this disturbance that's traveling through the stadium when you observe it. It's kind of cool. It's called the wave, right? You see that traveling around the stadium. But what you know is that it's not that like all the people are running around the stadium, right? Every person just when it's their turn, all they're doing is standing up and sitting down. So the particles or the people, yeah, they're just oscillating, say, pretend that's like little simple harmonic oscillators there. But you can see the disturbance moving in a way that is normal or perpendicular to the way that the particles are moving. So that's like my kinesthetic way to understand it. But whenever you're looking at these waves, don't forget that you're looking at some kind of physical disturbance. Okay. All right. So we're given this wave function. I gave it to you in this awkward way just because a lot of times wave functions are handed to students like this, and I want you to be able to deal with it. So um, you're given this particular wave function. Then I tell you here x and y are in meters, t's, and seconds. So we're assuming SI units here. But what I'm going to do now is I'm going to rewrite this with the units in it. Okay, I'm going to rewrite it with the units in it just so that we have that what that looks like. Y is a function of x and t, right? And we'll come back to that, those two variables there in just a second. So that 0.20, that's my amplitude, right? That's in meters. So now you can kind of start picturing this stuff. Try not to keep it at arm's length and just feel like you're doing math, right? Try to really kind of bring it in and interpret it so you actually feel like you're doing physics here. So sine of, now what is this? 0.19, and this is going to be meters to the -1 here. That's my omega, times x, and then minus, I'm sorry, that wasn't my omega, that's my k. I misspoke there. Seconds to the -1 t. Okay. So we dealt with omega is what always is multiplied by t, not multiplied by x, of course. So one thing you can remember is that inside the argument of the sine function, right, that has to be dimensionless, doesn't it, in there? Yeah, so if I have x, which is in meters, then I know whatever is multiplied by it needs to be in 1 over meters. And t, which is time, whatever is by it needs to be 1 over time there, because that needs to be dimensionless inside, remembering that radians are dimensionless. So what I'm going to do now, so that's how I would write that out. And if you're really kind of struggling to keep this stuff physical when you're doing these problems, express the units. I've been saying this all year, but I'm going to say it again. Express the units. That helps keep you closer to what the actual quantity is. It's not just a value, then it's a quantity. So the general form, let's go over this general form again. Actually, I'm going to swap out colors doing the general form. So here's the general form of the equation. And because this is the first problem like this we've done together, I'm going to really slow down and kind of talk about the anatomy of this particular equation. So y of x and t equals a sine kx minus omega t. All right. So first of all, what's the x and t about? Well, if we're considering like a water wave, right, or a stadium wave, whatever, you could think about the water. Y is where's the particle, as say your water particle say is oscillating up and down, right? Where is that particle of water? Now, where it is and what any particular particle of water is doing or any particular person in the stadium is doing depends on two things. Depends on X, where they are located in the medium, and T, what time it is. Another way you can think about this, maybe this is more straightforward, is thinking about a wave on a string or a rope. So in that case, you can think about one little particle of string and say there's a wave going along that string. Really kind of slow it down so you can see it. One little particle of the string, where is that particle at any time? Well, that's going to depend on, or when I say where, I mean like what is the displacement of that particle at any time from its equilibrium? That's going to depend on where it is on the string and what time it is. Okay, like when it's that particle's turn to be going through its little cycle. Yeah? Okay, so spend time on that if you need more time on that, because that's an important one. We already know what A is. A is amplitude, right? You should be pretty comfortable with that at this point. This K here, what's that? That's something called the wave number. What's the wave number? That's a weird one, right? So kind of spend a little time with the wave number and see, I don't know, if you can make it make a little bit of sense to you. I will often ask students what their interpretations are of the wave number, and there are different ways that students usually describe it. Something that I say to try to be helpful is you can think about it as the number of cycles per meter. And our equation for K, for this wave number, it has such a generic name, that's part of an issue. But our equation for wave number is that it's equal to 2 pi over lambda. So right away you're like, what? Because lambda, we all get wavelength, right? We're all pretty comfortable with lambda. We can see it, we can visualize it. So how do we do this thing with K? So I'm going to say it again. We can interpret it kind of as cycles per meter. So we often think about cycles per time, right? So now I want us to think about cycles per space. This is really taking the same idea, like how many cycles would fit into 1 meter. And if that helps you make it physical, then cool. All right, and then omega, of course, is our angular frequency. That hasn't changed. Oops, angular frequency. Okay, T is time. X is where you are on the rope. So your textbook has like gorgeous illustrations. I don't know that I'll try to do them. I guess for like my wave on a string, if I'm going to be thinking about a wave on a string example, something like this, I would have that my y would be the vertical, right? This is y, and my x is the horizontal. So you can see how if you are one particular spot, one particular particle in the medium, like one little chunk of that rope, what you're doing, like where you are above or below the equilibrium, right? How high, how low, where you are is going to depend on a couple things. It'll depend on where you are with respect to X, right, on the rope, and it's going to depend on what time it is. Okay, that I keep saying that because I want you to absorb that. It'll help you to physically interpret these equations better. And then reminding us again that radians are dimensionless. Okay, so we should feel pretty comfortable and like introduced to the wave function at this point. So let's start working through it. The best way to get to know it is to kind of work through it. This problem is really about like the anatomy of the wave function and how do we use it. So part A here asks us what is the amplitude. So the amplitude you can just read right off of the equation here, right? It would be this leading term, and that would be just checking like, does the student know what that leading term means, like what it does, right? So if any sine function will max at 1, make sense? So if I have just something that's multiplied by that sine function, now the sine function is going to, or now the entire function is going to max at that value. So that's how it controls the amplitude. So amplitude I can read right off the function, 0.20 meters. So that was just by, right, the term right in front of the trig function, that was by inspection. Part B, what is the angular frequency? So now again, I need to know the equation and know where to look. The angular frequency is the quantity that's multiplied by t there. So angular frequency is 46 seconds to the negative 1, or you can also write it as 46 radians per second. So if it helps you to keep that radians in there, if it sort of helps you to keep the quantity straight, do that. Radians are dimensionless. So what that really means is that we express them when they're useful and we don't express them when they're not useful. So usefulness can be about you too and how you're interpreting these quantities. So 46 radians per second. You'll see it written both ways. So I want you to be okay with it both ways. But when you have a choice, choose what makes most sense to you. Part C asks us for the wave number. Again, I can find that by inspection if I know what the general form of the equation is. It's the term that is multiplied by x. So I can see that k equals 0.19 meters to the negative 1, or again, we can write it as 0.19 radians per meter. Remember, it's we're looking at how much of the cycle fits in to 1 meter. Okay, I'm going to leave that at that. Part D, what is the wavelength? Well, the wavelength is not in our general form, right? The wavelength is not in our general form. There are a couple different ways you could do that, but the wave number, remember this equation up here relates to the wavelength. So wavelength, I would use that. Wavelength is equal to 2 pi over my wave number. So 2 pi, and that's really radians, right? Divided by 0.19 radians per meter. That gives me 33.1 meters as my wavelength. So, okay, now what probably happen, and this happens because wavelength is so physical, we can picture it so well, right? 33.1 meters, automatically your mind goes to like, wow, that's a super long wave, like compared to my size, right? 33.1 meters. Now you can picture this wave. So notice how important, first of all, pictures are to us, which is why I encourage you a lot of times to draw pictures. And just also notice that some quantities are much easier, much more intuitive to picture than other quantities. And those other quantities will become more intuitive the more that you work with them. Okay, last part. Part E asks for the wave speed. All right. Now, when I'm doing this in class, I kind of leave this here and I walk around and I see what my little groups of students are doing. And um, the most popular way to answer this one, you can pause the video right now, try to answer it on your own. But the most popular way to answer this one is students will look at the general form equation. They'll say, oh, velocity, I know how to do that. I take the first derivative of my position function. So they'll find dy dt. But wait, what is dy dt? Dy dt is the velocity of the particle as it's in simple harmonic motion up and down on the rope. That's what dy dt is. It's the velocity of the particle. And so, of course, you're going to get a sinusoidal function for that, right? Because it's in simple harmonic motion. So what you're going to find when you do that is you'll find the velocity of the particle. That's not what you want. This particular problem in this particular part is asking us for the wave speed, not the speed of the particle, but the speed of the disturbance. So this is what I was talking about at the beginning. That's really important to be able to separate those two ideas. The idea of what is the wave doing, the disturbance doing, and what is the medium doing. So reach out to me if you want to talk more about that, or if you need a little bit more when it comes to that. So this problem is asking us for the wave speed. So wave speed is equal to the product of wavelength and frequency. Super important equation here. This equation it's so cute. It's so simple. It's so straightforward, but it's really fundamental whenever we work with waves. I also know that frequency here relates to angular frequency, right? Is equal to angular frequency over 2 pi. So that's another equation that I know. So when I'm trying to express my V here, I can put those two things together and say, well, okay, V is going to be equal to lambda times omega divided by 2 pi. And when I sub in my values there for wavelength, I've got my 33.1 meters, omega, my 46 radians per second, divide that by 2 pi radians, and for my wave speed, I get 242 meters per second. And right away I noticed that like, oh, so that's a constant. Yes, it's a constant. That wave speed is going to be a constant value. There's only one thing that can change the wave speed. Only one thing, and that is if we change the medium. I'm going to say that again. There's only one thing that can change the wave speed, and that is if we change the medium. The wave speed depends on the medium only. The wave speed depends on the medium only. So this is a really common place for students to fall down. What they'll do is students will sometimes look at this equation right here and let this equation kind of like shape their reality and say, well, no, look at the equation. In the equation, velocity depends on wavelength and frequency. So if I change the wavelength, it'll change the wave speed, right? My answer is no, it will not. The only way to change the wave speed is by changing the medium. So if you don't change the medium and you have a different wavelength, that means frequency, you'll have a different frequency. And actually, wavelength is kind of like the dependent here. The uh, yeah, wavelength is like the dependent thing here. Frequency would be more likely what you would change. So for instance, if you were propagating a wave in water or on a rope or whatever, you would propagate it at some particular frequency. You can have a mechanical oscillator. You could be like waving your hand back and forth, and that would be a frequency, right? A certain sound for a sound wave, a certain hit, a particular key on the piano, that will give you a particular frequency. So frequency depends on the source of the wave. Frequency depends on the source of the wave. Wave speed depends on the medium the wave is traveling through. And wavelength adjusts. I'm going to say that one more time. Frequency depends on the source of the wave. What key on the piano you're hitting, how fast you're moving the rope up and down, how fast you're splashing your hand in the water, right? The source of the wave. That's what frequency depends on. Wave speed depends on the medium you're in, and wavelength adjusts so that this equation will hold. So if I have, say, an air, say, let's just talk about a sound wave for a second. If I have a sound wave in air and I hit a particular key on the piano, that's some particular frequency. Whatever key I hit on the piano, I don't change the speed of that sound wave through the air as I'm hearing the sound, right? That is dependent on the air in the room. The air is the medium, that's why I say that the sound wave would be traveling through. So the wave speed is set by the medium. The frequency is depending on the source. And what that means is as I hit different keys on the piano, automatically the waves traveling through the air have different wavelengths. Different frequencies are going to have different wavelengths. But when you take the product of wavelength and frequency, it's always going to be equal to the wave speed that is set by the physical medium the wave is traveling through.